Now let's look at this figure 24-1. And let's just start with a transformer. To impedance, 2%. Now, notice 2% impedance is very low, so the short circuit current at the transformer would be high. Now, if you had 4% impedance, then the amount of short circuit current at the transformer would be cut in half. So impedance is, you need to know that, because the higher the impedance, the lower the short circuit current. But the lower the impedance, the higher the short circuit current. So keep that in mind. Now, and the only thing that's going to reduce the short circuit current to the equipment is the length of the conductors and the size of the conductors when you do the calculation, which we do in our Stallcup's electrical design book, volumes 1 and 2. We show you how to do that so you could actually do it in the field real easy. Now, note 1, all systems over 1,000 volts are supplied with 90 degrees C terminals, and you'll be using medium voltage or higher voltage. But notice those terminals are 90 degrees C, 110.40, specifies that. Now, the conductors in the conduit or cables, you're going to go to the new Article 311 to determine those ampacities by using one of those tables that deals with your installation. But now the switchgear, the components, and everything in the switchgear, you go to Article 490. And with what we see here in this illustration, you can see 490.47, 490.35A, 230.210, and 110.30 would pick up some very important information in the NEC sections reference there. And then notice when you review the supply voltage, it's 13,800 volts, which is 13.8 kV. That's his switchgear supply voltage from the transformer. Then notice the number 1 disconnecting means, an overcurrent device there, is a feeder going to a transformer, and they're stepping the voltage down to 480, 277, 3-phase, 4-wire system. If you look at overcurrent protection device number 2, it's going down with 13,800 volts or 13.8 kV to the switchgear 490.47. We'll give you some information about that. And then when you look at feeder number 3, we're supplying a transformer, and then we're stepping the voltage down to 208, 123 phase 4-wire system. See? And then when you go to figure number 4, I shouldn't say figure, but overcurrent device number 4, that's just reserved. It's a spare. And when we go over to overcurrent protection device number 5, it's feeding a transformer, and it's stepping it down to 480, 277, 3-phase, 4-wire system. When we go over now to overcurrent device number 6, well, that feeder goes down to a transformer, and the voltage is stepped down to 4160, 2400 volt, 3-phase, 4-wire system. And then notice all your 600 volt type conductors, or 600 volt rated or less in this illustration. And this is a one-line diagram, as you see listed in 90.8 and 490.48C. But 205.2 of NFPA 70E, and I'll say it again, 205.2, as well as D.2.2 in the Annex D in NFPA 70E, says you have to have a one-line diagram like this for safety, so that you can go in and isolate. You'd say, well, I want to work on transformer with that feeder number 1. Then just disconnect there at number 1, lock and tag it out in accordance with the code. And if that happens to be your disconnect by 14, then that's fine. You've isolated. And you'd say, no, I want to isolate the panel board. So you go to panel board, disconnect there, see, and you can isolate the power below, see, because you're disconnecting it. And so what this is showing is that you can isolate locations where equipment's installed to pull maintenance, repair, infrared inspections, whatever you may be doing, in accordance with NFPA 70B, Chapter 7, and the Annex L in NFPA 70B, if you want to review it, along with 205.2 and D.2.2 to the Annex D in NFPA 70E. So remember, one-line diagrams is to isolate locations where you want to work. Schematic diagrams are for troubleshooting, and that's exactly what your figure 24-1 is illustrating to the user of the NEC.